Hi, my name is Vinay, and with this experiment, we will see how you can write a code for 4-bit adder and perform simulation using Xilinx ISE software. So I'm using a Xilinx 14 series of ISE Foundation software. So here I have created a project in Xilinx ISE and using a Spartan 3 device. And here is my Verilog code, which is a very simple format where you declare the inputs A and B, a carry input, and the output like sum and carry out. So here I can just simply write cout comma sum, and I can just add them A plus B plus C, and that's it. A very simple code. Okay, and here is a test bench written. Okay, so where what I do, I just declare some registers as A and B, and here I write in sequence of inputs in simulation for simulation. So this is the initial value A, B, and 0. So I just after 15 nanosecond I initialize the value of 2 and 3 to AB and make the carry 1. Then later word I change it to 5 and 3 and make the carry 0 and make the carry 1 again after a while. So a simple one. So you can also change the code and make changes in the simulation as per your wish. So I set the project in simulation mode. Now you have to just double click the simulate behavioral model and it will open another app where you can see the simulation result. So this is the iSim simulator of Xilinx. So here you can see that it opens another application and you can just zoom out. So here you can see the simulation result, and I can just zoom a little bit, go and scroll back to come to the first one and make the radix of all the formats to unsigned decimal. So here you can see that 0 plus 0 is 0, okay, 6, okay, so here's my sum. So 2 plus here 2 plus 3 is 5 plus 1, which is carry, so that's why we get 6 over here. Now here at this point of time I make the input as 5 and 3, so the resultant would be 8, and after a while as I'm making the carry 1, so that's why you get the result as 9. Okay, so here I see that the simulation is going well, the code is working functionally perfectly okay. Now I just close this app and exit it. Now I come back to implementation mode and select my main design module. Now you can just synthesize, but before synthesize you can set the design goals and strategies which you want. So you can set that, okay, I want balanced performance or power optimization or timing performance, how you want it. So I've set the default value as like my timing performance, that should be the best. Okay, you can just say okay. You can just synthesize design and it will run for you. So he's going to implement and synthesize it for Xilinx Spartan 3 series of FPGA. So it just take a minute or two at the max. So here you can see on the console output all the results are coming. So he has mentioned that maximum combinational path delay is 9 nanosecond. So because as there is no sequential circuits, there are no flip-flops involved in the design, so that's why you will only get the combinational path delay. So that is nothing but the critical path delay also, you can mention it. Okay, now if you want you can see the entire design summary. Okay, so here you will get the entire design summary of the adder. So here you can see the number of slices being used and number of 4 input lookup tables, that utilization percentages, and the availability of the left resources. These are mentioned over here. So here you can see that if you want a detailed synthesis report, that also you can see. Okay, now out of date these values are because I have not implemented design, so I just run the implementation of the design also, so that we can see the update on these ones. If you want, you can see the detailed synthesis report, so you can go inside and see what is happening. So here you can see that, okay, how many lookup tables have been used and how many XOR with carry are being used, how many input of buffers have been used. So if you see any discrepancy, you can notify in your design and make changes accordingly. Okay, so here are the delays of each and every input of buffers. Okay, so that is what the delays are mentioned. So out of which 7 nanosecond is for logic, 1.65 is for routing. Okay, So that is how you can get a bifurcated timing delays. So as my design is implemented, I can just go back and see the reports. For example, you can see the timing report or the power report. So this is my power report. Okay. So the static power, he mentioned that is around 27 milliwatts. Okay. So this is an static power consumption. This is not active, because active you have to tell the software that how much amount of toggle, what is the toggle rate of the design. So accordingly, he has mentioned some default activity rate like flip-flop toggle rate 12.5% and IO toggling is 12.5. How much is output load? According to that, he will calculate the power consumption. Okay. So this is about 4-bit adder. Okay. Thank you very much.